Right, thanks, Les. And as I say, welcome everyone to another online meeting of the Royal Astronomical Society. Hope you're all keeping safe and well. And if this is your first time here with this evening, it's great to have you join with us. Firstly, I must apologise for my somewhat husky voice. This is due to sore throat and chest infection, which I've recently acquired, but happily I can inform it's not COVID related. Hopefully you can hear and understand me, but please shout out if you can't. As Les just previously mentioned, this is going to be, for the time being anyway, the last of our online-only meetings that we've been presenting over the pandemic period, and have basically been the mainstay of maintaining the momentum and the continuity of the Society since we were unable to meet in person. But now, as some of you may recall, we now have a new venue at the Thames Chase Forest Centre, and we have actually had a couple of meetings there, particularly for the young astronomers, which we held both in person and online, which proved to be quite successful. And that's the way how we're going to be going on from now on. But I'll speak more about that later. Les has covered the usual the housekeeping items for tonight's event, but just to add to that, after our presentation by our main speaker, we'll then continue with the Society's notices and announcements, followed by a general chit-chat regarding anything astronomy related, which you are all quite welcome to stay and join in with us. So I'm very pleased to welcome this evening's speaker, Professor Duncan Lorimer. Professor Lorimer currently holds the rank of Professor of Physics and Astronomy and serves as Associate Dean for External Research Development in the Eberly College of Arts and Sciences at West Virginia University. After graduating with a BSc in Astrophysics from the University of Wales in Cardiff in 1990, he got his PhD in 1994 for his contributions to Pulsar Astronomy while at the University of Manchester. Since then, he has held positions at the University of Manchester, at the Max Planck Institute for Radio Astronomy at Cornell University, and as mentioned before, at the West Virginia University. Whilst at West Virginia, he's received a Cotterill Scholar Award in 2008 from the Research Corporation for Scientific Advancement, and has received both college and university awards for excellence in teaching. He's been a fellow of the Royal Astronomical Society since 1994, and in 2018 was named a fellow of the American Physical Society in recognition of his contributions to our understanding of pulsars and for the discovery of fast radio bursts. As we learned this evening, fast radio bursts are millisecond duration pulses of unknown origin that were discovered by an undergraduate student working with Professor Lorimer at West Virginia University in 2007. And now, almost 15 years later, with hundreds of other sources currently known, an understanding of their origins is emerging, but still far from complete. So this evening, Professor Lorimer will tell us the story of their discovery. It will summarize what we know about them so far. He'll describe the opportunities these bursts represent and make predictions for what we might learn in the next decade. And his talk is entitled Fast Radio Bursts, an Evolving Cosmic Mystery. And before my voice gives out completely, I'd like to now hand over to Professor Lorimer.
Thank you very much, Les, and thank you everybody for being here. I really appreciate the invitation to speak. I would love to be in the UK myself. I'm originally from the Northeast in Darlington, so it's nice to hear some British accents this evening. So it's a pleasure to be coming to you from West Virginia, where I currently am, and to talk about these fascinating objects that we're studying in many different ways, and to give you a sense of the discovery and what's going on currently. So you're looking at a sort of multifaceted picture showing the Parkes Radio Telescope there. That's in New South Wales, Australia. And it's looking at this bright object here. This is, you know, what you would see with if you had radio eyes. It's this bright flash. It's trying to depict one of these bursts to get over the fact that they are incredibly bright relative to other radio sources. Here's the band of the Milky Way as seen in radio waves. And rather than seeing stars, you see mostly expanding shells of gas from supernova explosions that have littered the disk of our galaxy over the years. And what we're discussing tonight is a phenomenon that is not really connected with the Milky Way galaxy. They're coming from well beyond the Milky Way, although there is a nice connection that is emerging that I'll get to with objects in our galaxy. So just to orient us, before I dive in, I'm going to be talking primarily about objects in the radio part of the spectrum. So that is the long wavelength band where the photons of light have low energy compared to the visible and higher energy X-ray and gamma ray waves, which have shorter and shorter wavelengths. The types of radio waves that I study have wavelengths of about 20 centimeters in duration, so you can, in length, and so you can picture them in your mind's eye, perhaps. And we use large radio telescopes like the one close to where I am currently in Greenbank, West Virginia. And you can perhaps see this picture on my wall here showing Jodrell Bank in Cheshire, where I used to be at. That are situated on the ground. And of course, there are many other telescopes in the optical band that are often on high mountain tops to get above the clouds and where the atmosphere is thin. And also there are orbiting satellites that allow astronomers to piece together information particularly from X-ray and gamma rays that don't penetrate the atmosphere, fortunately for us, but allow us to measure that radiation from astronomical objects. And with this picture across the electromagnetic spectrum, we generally get much more information than just studying one wave band alone. However, I'll be fairly focused towards the radio band tonight. And I want to start with a little picture of the radio sky. And I hope this is going to work. I'm also going to play a sound bite as well. I'm going to, I've just turned that down, so hopefully you can hear my audio above the rumble in the background. So just to begin with, what we're looking at here is the sky above Greenbank, West Virginia, and it's not in optical light that we're normally used to. What you're looking at here is the sky measured if you had eyes that were sensitive to 5 centimeter radio waves. So that's quite a different picture that you get from the night sky with our regular eyes. Now, if you look at each of these dots here, they're not actually stars. In the radio band, we see mostly galaxies, distant galaxies. Here, these extended objects, those are examples of supernova remnants that I was talking about earlier. They're also quite visible in the radio sky. But mostly everything else you see is a distant galaxy. Now, you can hopefully hear things as well. There's this general rumble, that's the background hiss that's coming mostly from the sky and the electronics in the telescope. But then, if I just wait for a second. Okay, you heard a chirp there, sort of a high frequency tone that cascaded towards lower frequencies. And that's trying to depict a fast radio burst, how it would sound if you translated the radio signal into an audible tone. So they have, some of them have different durations and different brightnesses. So that's the phenomenon. And roughly speaking, every 20 or 30 seconds or so, one of those bursts will go off somewhere over the sky. And we've been seeing them now since 2007. So as I mentioned, they're relatively bright in the radio compared to other radio sources. We've observed them now all the way down to the FM band. So that's around 100 megahertz. That's where you would tune in your FM radio in the car, all the way up to a few gigahertz. And that's more where radio astronomers look. So a few billion hertz. And so you're going down to sort of centimeter wavelengths at that frequency band. And we have no reason to believe that to doubt that they could be observable at higher frequencies. We just haven't been able to do that technologically just yet. They come from random positions on the sky, and as I mentioned, they go off every 30 seconds or so, and so thousands of them are inferred to be going off over the sky each day. The problem with our telescopes is that we can only see we don't see the whole sky like we're looking at here. At any one instant, we just see some smaller part of it. So we often miss the objects that are going on outside of that field of view. They have this quality known as the dispersion, which you could hear in those audible examples. And I'm going to show you some images of those shortly. But it's a much higher dispersion than we observe for objects in the Milky Way, which infers that they are much further away, which is confirmed with other measurements. The pulses themselves that I will show you are very narrow. They're actually just a few milliseconds in duration, which immediately suggests that they're coming from something very small, a few light milliseconds across. So something very compact, like a small star is producing them, not a huge galaxy, which is thousands of light years in size. Just to get you oriented, excuse me, there's about 611 distinct sources that are currently published. About 24 of those are known to repeat. And about 20 of the fast radio bursts, and we call them FRBs for short, they have associated host galaxies. So that's where we're able to pinpoint the burst on the sky well enough to actually say definitively it's coming from this galaxy. And I'll show you some examples of those in a few moments. And then very recently, we were able to associate one of these sources with something that we know of very much about in our galaxy, a source called a magnetar. And I'll often use the we. It's a royal we when I speak tonight. So I'll be talking about not necessarily work that I have done exclusively, but we as in the astronomical community. So forgive me. I'm not trying to take credit. It's just a force of habit. Okay, well, to understand how we came to learn about these sources, it's worth going back in time to the mid-60s, when Jocelyn Bell, who was then a graduate student at the University of Cambridge in the UK, was working with her advisor, Anthony Hewish, who has, you likely know, recently passed away. Anthony, it was in the news lately. But Jocelyn is still very active. And at the time, she was working as a student, looking at the radio sky with this telescope here, which is an array of cables across a field that is acting as a giant FM receiver and is able to scan the sky in the FM band. And Jocelyn was looking for the twinkling of radio galaxies due to their passage through the interplanetary medium. It's a bit like the twinkling of starlight as it passes through the Earth's atmosphere. She was able to study that, but really by pure serendipity, she was also able to find these pulsars, these unusual pulse sources of radio waves. And you can see one here. This is a pen chart recording. So literally there's a piece of paper rolling along, and there's a pen that is recording the intensity coming from the radio telescope, so that you see you basically get a measurement of the radio signal from the sky as the Earth rotates and the sky moves across your field of view. The telescope is looking straight up in this case. And so Jocelyn was able to conclusively show that there were events, these pieces of scruff, as she called them, that were very distinct and repeatable over many, many nights, and were distinct from sources of interference that were locally generated. When they looked at one of these pulsating radio sources, these pulsars, with higher resolution, they kind of zoomed in on this scruff here. They were able to see that the pulses were coming very regularly, and that was an entirely new phenomenon that was very hard to reconcile at the time, but it was ultimately conclusively linked to neutron stars. So it's radio emission coming from stars that have exploded, the neutron stars that were produced in supernova explosions. And the picture that we have about pulsars today is that the neutron stars are formed in these supernova remnants, such as the one over here, which is the Crab Nebula in Taurus. And what you see today is an expanding shell of gas. And almost 1,000 years ago now, the ancient civilizations were able to saw this as a star in the daylight sky. And what you see now is this expanding shell of gas. And so what the ancient astronomers were witnessing was the explosion of a massive star, which formed one of these very compact neutron stars. And the neutron stars are very exotic stars. They're about the same mass of the sun, but only around the size of a small city like Morgantown, where I am. So something like 10 miles radius. But imagine the mass of the sun or more compressed into that small radius. You get this incredibly dense object, and it also has a really high magnetic field, and it's spinning very rapidly. As the pulsar spins, so we call these pulsars neutron stars, and I use that word almost interchangeably. So as the pulsar spins, as this neutron star is spinning, it's constantly emitting radio waves, and as the magnetic poles of the star sweep past our line of sight, we get these pulses of radiation, which we're able to pick up. And that's what Jocelyn was originally seeing there. These are the pulses of radio waves that are crossing their line of sight and arriving at the Earth. And so the spacing between the pulses is the rotation period of these pulsars. And they rotate anywhere from around close to a millisecond, so almost 1,000 times a second. They have a millisecond rotation period. And the longest one now is several tens of seconds, and all things in between. So this is not a talk about pulsars per se, and you've probably had talks about those in the past, and that would be an interesting topic to get into in the future. I raised the topic of pulsars tonight to motivate what happened with fast radio bursts. And that's because when people in 1968 started to study the pulses that were coming from the Crab Nebula, they quickly found pulsing signals from this region in the sky. They found a very steady source of radio waves that were produced 30 times a second. So the star is spinning with 30 times each second on its axis. And it's producing a very steady stream of pulses. But every minute or two, or 5 or 10 minutes, you get this incredibly bright pulse here and here and here that are many times greater than the average pulse. And this is a train of radio data that's been superposed onto this image to kind of create this picture in your mind's eye. So imagine the radio signal is coming out of this this supernova remnant, and it's the encoded in here are the pulses from the pulsar, but occasionally the pulsar will emit what's called a giant pulse, which is many times the average pulse. And these pulses are so bright that they could be seen from well beyond the Milky Way. So even as long ago as 1968, the astronomers realized that it could be possible to detect individual pulses from sources like this that were in distant galaxies. And people started looking for them and thinking about what they might be able to do for us. And I just wanted to show you this paper back from 1973, which is basically what we're able to do now. But in 1973, this Russian theorist Ginzburg proposed that these flaring radio sources well beyond the Milky Way could actually be used to probe the gas between galaxies. That's exactly what we're able to do with fast radio bursts today. And I'll show you a little bit about that in a few moments. But the picture that we have now, we're here on the outer spiral arms of the Milky Way. And looking out into the universe, we see these fast radio bursts all across the sky. And by measuring the radio signal, we're able to probe the content of the material along the line of sight. It's between us and the other galaxies. So it's amazing that this prediction has come true and been fulfilled almost 50 years later. So people back in the 1970s were searching for these radio sources. Here's one particular search from 1979 that was unsuccessful, but it was motivated by astronomers thinking of other sources that could produce radio pulses. And so for those of you who are familiar with Stephen Hawking's work on black holes, Hawking predicted that black holes formed in the early universe could actually be evaporating today. That is, they lose mass over time, and eventually they lose all of their material. And in the final stages of that, they could emit quite a significant amount of energy across the electromagnetic spectrum. And so astronomers have been searching for events like that for a long, long time. And these two characters here, this is still Finney. This is a more recent picture of him. But back in 1979, he was a high school student working with this person here, Joseph Taylor, who's now a Nobel Prize winner for his work on pulsars. So it's an example of a high school student working with a professor, which is now very common in this day and age. But back then it was quite unusual. So people have been thinking about this for a long, long time. So when we came along and found fast radio bursts, as they're now known today, here's a picture of me and my student David back in 2007. This seemed like a new phenomenon, and it was, but it was the result of years and years of work. So I myself have been spending a lot of time studying pulsars, and back then we were particularly interested in looking for pulsars with the Parkes telescope in the Magellanic Clouds. And so we carried out a survey of some archival data, David and I, and we found this incredibly bright pulse, which I want to show you here. So this is the first fast radio burst, and it's what you're looking at here is frequency, so radio frequency versus time. And if you look at the legend here, this is about 500 milliseconds. So you're looking at about half a second of time here. And the radio frequencies are in the gigahertz part of the spectrum. So imagine tuning a radio receiver around the gigahertz band. And this is a very favorite band for radio astronomers. In any case, this black line that's streaking down the plot here, that's the That's that tone that you were listening to earlier on, and one of these fast radio bursts. And when you add up the signal along this line here, you get this very bright pulse. And the width of the pulse here is just a few milliseconds in duration. So that's what I'm talking about when I talk about these fast radio bursts. This is basically what you see. You get this just tiny little snapshot of data, and then it's gone. And so we got really excited about this because it was much brighter than we were expecting to see. It followed all of the characteristics of the pulsars, except that its dispersion was much greater than we would expect for the Magellanic Cloud. So we wrote up the results of our study and boldly proposed it as the prototype of a new class of radio sources that we proposed were of extragalactic origin beyond the Milky Way. And we were able to not measure directly the distance to the burst, but we were able to estimate it, that it could be as far as 1 billion parsecs away. That's a few billion light years away. So in the really quite distant universe. How did we know that? Well, we had a really powerful tool to estimate the distance, and that's by analyzing the plot in a little bit more detail here. So I've put this little blue triangle on the plot here now. So you can pick these two vertices of the triangle here and go from one end to the other to sort of trace out the burst. And you see that the time delay between these two frequencies is about 200 milliseconds, just a little bit over 200 milliseconds. That time delay is proportional to a quantity that astronomers call DM. It doesn't stand for dark matter. It's what radio astronomers call dispersion measure, a little bit of jargon. In any case, the DM or the dispersion measure serves as a proxy for the distance. It's like a yardstick that we're able to estimate the distance with. Basically, what's happening is that in his an artist's impression of the fast radio burst traveling across the universe and arriving at the Earth, what's happening is that the highest frequency signals of the radio, the content of the radio pulse, travel faster through the ionized medium between us and the fast radio burst compared to the lower frequency signals. And so the highest frequency waves arrive first up here, and the lower frequency waves arrive later. That's because the space between us and the fast radio burst is not a vacuum. There is a small amount of ionized gas, basically just free electrons in the universe that are causing the radio waves to move at different speeds. So the further away the fast radio burst is, the more dispersion it will experience, and the greater the delay, and therefore the greater the dispersion measure. So we measure this DM for any given burst, and it has a number that's typically between 0 and a few thousand, that sort of order of magnitude. And what we can do, and I'll show you in a moment, is to estimate the distance directly from that. Anyway, so that's how we knew that these sources were much further away than the Milky Way, but that we only had one of them. And so it took quite a few years for the story to get to develop, and there was a lot of speculation about whether the one source was perhaps just a source of interference, or really a prototype of a new population. And it turned out to be the latter. Around 2013, astronomers produced these results, announcing 4 new bursts or radio pulses that are shown here. And you can see them in this diagram here, along with our original burst and another one that had been found in the interim period. So we'd gone from 1 burst to 6 in that time. And what you're looking at here is the dispersion measure, this dm quantity that I just introduced, plotted against the galactic latitude. So that's the angle away from the galactic plane. If you imagine we're sitting on the galactic plane, and as you look away from the galactic plane, you can trace out an angle. This dispersion quantity is very well understood for pulsars which inhabit the Milky Way. And those are these red points here. These are the known pulsars in the galaxy. So they inhabit this part of the diagram, whereas the fast radio bursts have much, much greater dispersion measures than you would expect from being associated with the Milky Way. And so that was what was really giving us confidence that these sources were at cosmological distances. And so this paper is a real landmark for us. The fast radio burst term was coined there, and the introduction of them as a cosmological population really began almost 10 years ago at this point. So I must step back for a second and just introduce one more concept to you, and that's the idea of cosmological redshift. And this is a very important quantity and is probably known to a number of you who've studied astronomy in various ways, but perhaps not known to all of you. It's really important when you're studying sources that are well beyond the Milky Way, because in the time that it takes for the source to travel from where it started to where it gets to today at the Earth, it's traveled across a significant fraction of the extent of the universe. And the universe is not just a static entity. The universe itself is expanding. And so rather than the source, the position between, let's say, that the fast radio burst comes from this host galaxy up here on its way to the Earth, by the time the pulse arrives at the Earth, both the host galaxy and the Earth, the separation between them has increased. And the size scale of the universe has increased because the universe is expanding, as we learned from Edwin Hubble almost 100 years ago when we discovered that the universe was expanding. So this is a very well understood phenomenon that's really reflecting something significant about our universe. What it means is, though, that the wavelengths of the radio waves get stretched as the universe itself expands. And so you might get a wavelength here at emission. By the time it gets to the Earth, it's been stretched out by the expansion of the universe. And we measure this, the amount by which it's been stretched, and we call that the redshift, or this Z over here. It's the observed wavelength minus the emitted wavelength divided by the emitted wavelength. So this is about the one equation that I'll show you in this talk. So you can think of it as the fractional increase in the wavelength. If you look at that expression for a second, you'll realize that lambda emit divided by lambda emit is 1. And so you can move the 1 over there next to the Z, and then you get 1 plus Z is just equal to the ratio of the observed over the emitted wavelength. So what does all this mean, you might ask? Well, if the redshift Z is 0, 1 plus 0 is 1. That means that the observed wavelength is equal to the emitted wavelength. If the redshift is 1, let's say, then 1 plus 1 is 2, right? So that means that the observed wavelength is twice as big as the emitted wavelength. And fundamentally, what that means is that the universe has expanded to twice its original size during the time from emission to reception. So this redshift parameter Z is actually tracing out the distance to the source. And for the fast radio bursts, we actually have, from our understanding of how material is now distributed in the universe, we have a good rule of thumb. Whenever we get a fast radio burst and we measure its dispersion measure, we divide that number by 1,000, and that 1,000 comes from other measurements that astronomers have made. I'm not going to get into all of the details there, but let's say you have a fast radio burst with a DM of 800. You divide 800 by 1,000, the redshift would be 0.8. And then you can estimate from the redshift how far away that particular source is. So that begins to help astronomers try to figure out not only how far they are away, but also how much energy has been released. Because when you have an idea of how far away they are and how much energy you've received, you can backtrack that and estimate how much energy was released in order for us to get what we actually see. So some of the energy releases here are quite impressive. 10 to the power 33 joules is released by some of these distant sources of that order. By comparison, the sun is emitting 10 to the 26 joules of energy every second. So it's greater than the sun emits in the optical light. These sources are very energetic. So people started getting really excited about them. You know, we'd seen 5 or 6 sources at this point. They were all observed by a single telescope, the Parkes radio telescope in New South Wales, Australia, that I showed you at the beginning. People started wondering, well, surely they must be observable at other telescopes. It's not just, connected to Parkes. And eventually there was enough of the sky was covered by other telescopes that they began to be seen elsewhere. And this one here was found in 2014. You can see the pulse here just faintly against the background noise, is frequency versus time. And we call the FRBs now, we name them after their arrival time at the Earth. So this one arrived in the year 2012. November is the 11th month, so the second day. So this was the 2nd of November 2012. This source was detected by the Arecibo telescope, which sadly now no longer exists. It was in Puerto Rico, but it was eventually analyzed and published in 2014. So that was really exciting because we had a source that was now seen with another telescope, not just Parkes, and more of them followed. What was also really exciting about this particular source was that it repeats. All of the other ones up until that point were just seen once. People then pointed the telescope back at the source for many hours and didn't see any follow-up bursts. With this particular source, they did the same thing, but eventually they started to see repeat bursts. So that's really interesting, because what it means is whatever's producing the radio emission can't be just a single cataclysmic event where, for instance, a star explodes. That only happens once for that particular star, or 2 stars spiral in on each other and then coalesce to form a larger star and emit energy. Again, that only happens once. But something more sporadic that can happen multiple times, such as a giant pulsing emitting source of the one that we see in the Crab Nebula, well, maybe that's a possibility for this type of source. So it allowed astronomers to narrow down some of the sources of what these fast radio bursts could be. So that was great. It was seen with a different telescope. It repeated. The other thing that was really great about this source was that once we knew that it was going to repeat, we could really try to pinpoint it on the sky. And so what a group of astronomers did a couple of years after that was to stare at that position on the sky with one of the world's highest resolution radio telescopes. This is the Very Large Array in New Mexico. And it's an array of 26 dishes that essentially forms this giant radio eye that's able to really pinpoint radio sources on the sky. A typical radio telescope, such as Jodrell Bank or Green Bank, close to where I am, that can kind of pinpoint a star, a radio source on the sky to about the size of the full moon, or a little bit better than that. It's often not very good in terms of telling you exactly where it came from in the sky. And so that doesn't really help you, because when you look at the sky with an optical telescope, you see galaxies and stars and all sorts of things in that area. So you can't say that it came from that star or that galaxy. But once they found some repeat bursts with this telescope, they were able to dramatically reduce the patch of sky where the source could come from. And they localized it to just this host galaxy here, just this little fuzzy blob here. So this is an optical image showing a dwarf galaxy. And in fact, the localization is inside the dwarf galaxy. It's even better than this circle suggests here. The redshift of that particular galaxy, that's something that astronomers are really good at measuring. And this is why I introduced redshift to you. The redshift of that is 0.19. And when you figure out how much distance that corresponds to, it's a distance of 2.3 billion light years. So that's the distance to that galaxy. So this was fantastic. We now had the first definitive proof that fast radio bursts were not only coming from beyond the Milky Way galaxy, we'd measured their distance directly. We also localized them to a galaxy. And so we could say that they were coming from this type of galaxy. And then as the decade progressed, more and more telescopes, which are still in operation, started to come online. Here's one known as ASCAP, the Australian Square Kilometre Array Pathfinder. And it's also an array of dishes. This is in the Australian outback in Western Australia. And it's part of one of the next generation radio telescopes. And it turns out to be really good at finding fast radio bursts as well. Here's a picture of a bunch of fast radio bursts that it found. And it was able to establish a relationship between the energy of the fast radio bursts and the dispersion measures. And it was able to show that the more distant dispersion measures were generally less energetic. That's just because they're further away. So it's not that they're intrinsically less energetic, it's just that they're weaker as seen from the Earth. So it started to started to get us thinking about fast radio bursts as a population. What's really taking the astronomical community by storm these days is a telescope called CHIME, the Canadian Hydrogen Intensity Mapping Experiment. These astronomers like their acronyms, don't they? So this CHIME is an interesting telescope. It's not an array of dishes, it's an array of cylinders. And these cylinders are lying on the ground here in British Columbia, in the western part of Canada. There's 3 of them lined up next to each other. And what they're able to do is they're able to survey the sky as the Earth rotates. And unlike all of the other telescopes that have come before them, they're outfitted with about 1,000 different receivers, which allows the telescope to look at a very large swath of the sky, much, much larger than the full moon, which is about a degree across. It allows us to see hundreds of square degrees at a time. And this has allowed this telescope to find a whole bonanza of radio bursts. This is a little graph showing the number of radio bursts known as a function of time. So the first one was actually in data taken in 2001, even though it wasn't discovered by us until 2007. And then here were the first ones discovered, and you started to find more. And then suddenly, bang, the number of fast radio bursts just shot up in the middle of 2018. What happened was that CHIME switched on, and it started finding, this is a zoom in of this area here, it started finding about 3 of these fast radio bursts every day. And then it's still actually switched on. They haven't released their second catalog. They got so many bursts that they said, okay, we have to release the catalog of these pulses to the community. And so that's basically where we're at right now. We've got over 700 different detections of 600 plus multiple, 600 plus independent sources. So that's fantastic. CHIME has now started to show the fast radio bursts as a population. And so there's a lot of follow-up work going on. And I just wanted to highlight a couple of things in the final couple of minutes here. And one thing you can see many examples of this now is that fast radio bursts are being associated with many different types of galaxies. Here's a fast radio burst coming from the outer arms of a spiral galaxy that looks just like the Milky Way. This one is at a very low redshift. It's only 350 million light years away. Only. We often take these large distances for granted, but it's in the terms of the universe, it's a relatively nearby object. It's also periodic, which is very interesting. And by periodic, I mean every 16 days, it kind of switches on, it becomes active, and it sends a bunch of pulses out, and then it switches off. So something is happening here in this system that has a 16-day cycle. And that is, there's a couple of other examples of those that have been found recently that are causing astronomers to come up with models with binary stars, where you've got perhaps a neutron star going around a companion, and every 16 days it gets close enough to interact with material and send out pulses. Or perhaps there's a precessing model where, like the Earth, which precesses around its spin axis, neutron stars are also thought to precess as well. And so their beams come in and out of the line of sight. So this is still ongoing work, and we don't know what the cause of the periodicities is yet and how common they are, but it's starting to become an interesting phenomenon. And the final sort of really hot result I want to show you, actually a couple of more results, is one from last year where a fast radio burst was seen from a magnetar. And these are these extremely highly magnetized neutron stars. Here's an artist's impression of one. Kind of like the sun has sunspot cycles, the magnetars have cycles of their own where their extremely magnetic field occasionally snaps on the surface and releases large amounts of energy. And this giant radio pulse was found last year by a couple of telescopes and traced to a galactic source. And so for the first time, it looks like there's a connection between fast radio bursts and magnetars. And the big question now is whether they're all due to magnetars or whether this is just, one part of a larger phenomenon. And so there are many results like this coming out. Here's just another one I wanted to quickly end with from this year. We're seeing again a relatively nearby fast radio burst coming from the galaxy M81, Messier 81, and it turns out that the burst is actually coming from one of the globular clusters in M81. So not only do fast radio bursts inhabit other galaxies, they also inhabit globular clusters as well. So they seem to be a very ubiquitous type of phenomenon. And there's a lot of open questions right now in the community as to what they could be. Here are just some of the things that I'm pondering on right now, along with many others in the community. Do all of the fast radio bursts repeat? We don't know that. There's quite a lot of evidence now to suggest that the repeater pulses, those sources that actually repeat, have different characteristics to the ones that we've just seen once. If that's true, how many populations could there be? Could there be different types of repeating and non-repeating sources? Or even within each category, could there be different types? we could be looking at a very large zoo of possible sources that send out these radio pulses. It might not just be one particular phenomenon. Connected to that are the host galaxies themselves. As I just mentioned, the fast radio bursts are associated with all types of galaxies, spirals, ellipticals, dwarf irregulars, and now they've been seen in the Milky Way and globular clusters of a nearby spiral galaxy. So they seem to be produced in many different environments, which makes it challenging to have a single source phenomenon. And the different classes, if there are different ones, will occur at different rates. And so as these samples emerge, astronomers will be able to categorize them and study their relative abundance, and that will provide more clues. Undoubtedly, these periodic sources are going to add to the story. We don't yet know whether all of the repeating sources are periodic. And it's really quite hard to carry out these observations. You have to follow these sources for many months and years in some cases to detect the periodicity. So it's going to require a large amount of resources to do this. And we should prepare ourselves for surprises that might lie ahead. We haven't yet seen, for instance, optical flashes from a fast radio burst or gamma ray flashes that are coincident. That would be fantastic. We might see a release of gravitational waves from fast radio bursts in the future. And these are some of many surprises that could happen in the coming years ahead. So there's really a bright future to all of this, thanks to many different telescopes around the world. Here's the Fast Radio Telescope in China, which is now the world's largest dish. Here's one in California, the Deep Synoptic Array, which is, you're just seeing 4 of a very large number of dishes that are getting built out right now. Here's a dish that I'm using, a 20-meter dish at Green Bank. The nice thing about fast radio bursts is that they can be seen with large telescopes and with small telescopes. And so there's room for everybody to make a contribution. So I just want to stop there and thank you for your time, and also thank you for supporting science in general. I'm a scientist. I rely on funding support from the U.S. government, the state government, private foundations, and as I've followed my academic path, I've spent time in the UK where the same funding model is in place, and so really we rely on the taxpayers to support this work, and not everybody will become an astronomer, but through astronomy we hope to excite people about science, and that's really important these days. And so I'll stop there and take questions. Thank you.
Right. Well, thank you very much for that very informative and fascinating talk on fast radio bursts, discovery, history, and the work that's currently being carried out with it, Professor Lorimer. We were very fortunate, you may have been aware, to actually have Jocelyn Bell-Burnell speak to us last year. And so it seems fitting now that we've gone on to the next stage, so to speak, with the presentation from you and your work, which obviously led on from the Pulsar connection. And so we are really getting all the information and the latest is this information and research carried on. So I appreciate that, and thanks very much. What I'll do now, as is the tradition on our group, is if I can ask all the membership this evening to unmute their microphones, and if you'd like to please show your appreciation to Professor Lorimer in the usual manner, please. Right. Okay. Right. So, Professor Lorimer, if you're in a position to answer, we have a few questions in our chat here, if you have the time.
Yeah, I've got a few minutes. Love to talk some more.
Okay, right. So these are questions that obviously were introduced by the participants during your presentation. Yep. So It may be one or two of them have already been covered, but I'll just basically go through them. The first one we have here is from Andrew, who asks, if you can only look at one source at a time, how can you identify a repeating source? Can you miss repeats like this?
Yes, so it's quite possible that we'll miss repeating sources. The telescopes have a wide variety of capabilities. Some of them, they only see a small patch of the sky, and so you're reliant. Once you find a fast radio burst, you might take some telescope resources and look at that one night after night. But when you're not observing, the chances are it could go off and you would miss that. And so you have to kind of take this into account and collect these long streams of data and make a statistical argument as to how often the source repeats. And so that's the reason I think that the periodicity question is so fascinating, because it may turn out that 5 years from now we'll find that almost all of them are periodic. We just haven't collected enough data. Or it may turn out that we collect so much data on some of them that they just show really different phenomenon. So we're just beginning that phase of repeating follow-ups, I think.
Okay, I have another one here again from Andrew, and he's asked, with the large amounts of red shift, do you use a wide observation frequency window? Do you look outside the radio astronomy bands?
We're just at the mercy of whatever radio frequency band we've got, and so we're making the reasonable assumption that the fast radio burst is emitting over a very wide range of radio frequencies. That's certainly what we see of the sources that we've studied in detail. So it doesn't actually matter too much as to which part of the spectrum gets redshifted into our band. Yeah, that's the short answer to that question.
Okay, fine. Next, we have a question from Lee Campbell, who's over in Texas on your side of the water. In general, he's asking, he said, can you recommend an introductory text on the principles of radio astronomy?
Yes, I can. And I just grabbed one from my bookshelf. It's my screen thing is messing it up. Anyway, I'll post this in the chat. It's called Essential Radio Astronomy. And it's by James Condon and Scott Ransom. If you just Google it, actually, you'll find it. There's a free version available online. Now, when you say introductory text, this is assuming sort of undergraduate physics knowledge. So it depends how introductory you want to go.
I was looking at undergraduate physics level, yeah.
Then I think you'll find this to be very accessible. It actually, it tries to be self-contained, and so it motivates a lot of the arguments from first principles. So I think this is a really good one for you to dig into, and others.
Duncan, have they sorted out the issues with the second edition of that? There's been lots of reports of the second edition available on Amazon, missing many of the pages that are quoted to be present.
Oh, I had no idea about that.
The second edition includes a lot of extra chapters, apparently, and a lot of people have been not buying it because of that.
Well, so I didn't even realize there was a second edition, because the first one came out in 2016.
Well, just a word of warning to people who are thinking of buying. Just check out what it says on Amazon.
Yeah.
It's a bit worrying. Lots of people said the copy they've received, it appears to be missing several chapters.
Right, and I would definitely, with this particular one, I would start with the free online version, because it's everything in the book is online.
Yeah,
so
it's excellent. I've got a copy of it.
Good. Yeah, it really is. I teach from it when I have the opportunity to teach this subject, so it's really good.
Okay, well, thanks for that, Don, and hope that's what you're after, Dick. Okay, we have a couple of questions from Peter now, if you've still got time with us, Duncan.
Yeah.
First of all, and I think this might have been answered subsequent to Peter putting the question on chat,
Yep.
but he said, could there be different types of FRBs, some of which repeat and some do not?
Yes, I think that's the way the evidence is starting to build. And I didn't show this in the talk per se, but when you look at the sort of portraits of the FRBs, if you will, the frequency versus time, you see that for one, the repeating pulses are broader on average than the non-repeating ones, and they also have different spectral structure. They tend to be just concentrated into small parts of the band, whereas the non-repeating ones are visible across the band. So that type of morphology is really hard to explain with in any other way than different types of sources. So
Okay.
that's the latest on that.
Right. And as I said, there's another one here from Peter again. He asked, could FRBs be stars being swallowed by supermassive black holes, and the repeats are another star being swallowed up by the black hole, I assume?
Yeah, many of these types of models are actually possible. And so it's, at one point there was, the short answer is yes, you could probably come up with a model along those lines. The more nuanced answer is that, do those situations actually arise in the universe? And so about 5 years ago or more, when there were only a dozen fast radio bursts known, there were 60 or more theories, so more theories than bursts. And that's because there wasn't that much known about the fast radio bursts at that time. But over time, as more and more information has come out about them, some of those theories have been thinned out. The magnetar one seems to be really quite strongly favored now, because it has a mechanism that's been studied elsewhere that you can kind of build upon. And so that's really helpful. And then you can also infer how many magnetars might be in that particular environment and so on. So yeah, there's lots of open questions though. I think, we tend to think of them, or at least I tend to think of them, as something to do with neutron stars, because neutron stars have a lot of inherently good ways to release energy. Things crash into them, or they, gobble something up or whatever. But they could be something more esoteric. If neutron stars weren't esoteric enough for you, you could have these cosmic strings, as they're called, the relics of the early universe inflation that have been greatly stretched out. And there are theories where these, and they're basically just large-scale defects in the structure of the universe. If cosmic strings begin to interact, then you could get these pulses. So there's lots of ways to produce them, and so we just need to let the evidence build, I think, and see what we see how things go. I think in 5 years there'll be a lot more consensus about the repeating FRBs and the non-repeating ones.
Okay, thanks. This is one that's on behalf of my namesake, Les Brand.
Yeah.
Again, I think you may have covered this after he asked the question, but I'll go through with it anyway. Les asked, does there appear to be any correlation between the type of FRB and the type of galaxy from its origin, the morphology or the AGN status, etc.?
Yeah, so that they're to the extent that we have still rather limited statistics. The first thing you can say is FRBs coming from all different types of galaxies. They're not just seen in one type. So then do they break up in some way? Tentatively, it looks like the ones with these periodicities actually might be more preferentially seen in dwarf galaxies. But again, it's only 2 or 3 sources at this point, so I would hesitate to draw any strong conclusions from that.
Okay. And the last one I have for you, if that's fine, again from Peter, could you say something about the possible use of FRBs as a cosmological probe? Yes,
I think it goes, beginning with what I mentioned from that paper from 1973, that's that prediction has been confirmed. And so we've actually used fast radio bursts to directly measure the electron content across the universe. So that's like, you can't really do that in really any other clear way. So that's one, we're probing the electron content. As we get more and more of them, we'll be able to see turbulence in the intergalactic medium. So variations around an average density will start to become apparent. Many of these types of applications have been studied for pulsars in the Milky Way. And a way you can think about FRBs is that they're just like kind of a similar phenomenon, but allowing us to do things on a much grander scale. So the other thing that's kind of tantalizing right now is that through measurements of the polarization content of the radio waves, it'll begin to be possible over the next few years to start to constrain the magnetic field along the lines of sight throughout the universe, which again, we haven't really done at this point. So there's lots of interesting experiments like that to be had. And, we're just really beginning those. And the nice thing I'll just say finally is we don't need, for any of those cosmological applications, we don't actually need to know how the FRBs work. We just need to be able to find them and measure their redshifts. So that's a bonus because we might never know how they work.
That is a possibility, isn't it? That even over time and years and all the research carried out, we still don't get a definitive, which will be a shame, but I can see it. I'm always optimistic, and we've made a lot of progress with pulsars over the years, but there's still a lot of things there that, cleverer minds than I have yet to figure out. Do you think it would be an unexpected or unseen advance in science itself or technology which might bring about the answer, or are we going to be just researching?
I think, one thing that has really improved over recent years is the ability to do really detailed physical simulations on computers, and so they can start to really model the what we call the pulsar magnetospheres, the atmospheres of pulsars, and do really kind of groundbreaking work that wasn't possible 5 years ago. So yeah, I think that is there is a lot of hope there, actually.
Okay. Well, on that then, I'd like to thank you once again for spending the time with us to answer our questions. Again, once for a wonderful talk.
Thank you.
Wish you well with your future research, and hopefully sometime in the future you may get your answers you're after.
Yeah, so, I'll let you know if I do.
And the rest of the world, please. So, ladies and gentlemen, again, one more time, if I can ask you to unmute your microphones, and just one more time, show your appreciation for Professor Lorimer.
Thank you very much. Thank you. Appreciate it.